Well, folks, we got a really nice motion question for you today. Unfortunately, it's not calculator active, but when we start talking about motion, we're picturing three functions. We kind of start that hierarchy with the position function. His derivative is the velocity function, and then the next derivative is your acceleration function. And how all of those functions kind of interplay with each other is a monumental concept here in our calculus curriculum. So as we look at this problem, we've got two different particles traveling along the x-axis. Our domain is from 0 to 8, and our first particle is p, and they gave us his position function. Now check this out. The second particle is q, and they didn't give us his position, but they gave us the velocity function there. And then, of course, this fun little tidbit that q's position at 5, or the position is 5 at t equals 0. So first things first, let's see, when is particle P moving to the left? What I'm thinking is anytime, let's say, whenever the velocity of P is less than 0, that would imply that P is traveling to the left. So let's derive this position function they gave us for particle P, and we could say the velocity of P is going to be du over u. So I got 2t minus 2 all over that t squared minus 2t plus 10 function. Now, what I want to do with this velocity is set it equal to 0, basically identify all the critical points I can. And not only am I setting the numerator equal to 0, which is going to produce t equals 1, but I should also be entertaining the idea of setting the denominator equal to 0. Now, I was really hoping that that denominator was factorable, but what you'll notice is you can't factor this bear, which makes me very suspicious that the roots are imaginary. And now if you want to verify that, we're just going to calculate our discriminant, if you remember from that old quadratic formula. And in this case, you're going to get 4 minus 40. And that negative number, anytime the discriminant's negative, it guarantees that the roots are imaginary. So basically, there's no other critical points other than t equals 1 that we need to concern ourselves with. And what's really, really nice is that this t squared minus 2t plus 10 is guaranteed to be positive no matter what you substitute for t. So let's go ahead and make our sign chart with t equals 1. Remember, the domain is 0 to 8, so I don't want to continue this infinitely. And we've got the velocity of p. So substituting like a 1/2 in for this t up here is going to give me a negative answer. Notice we know the denominator is already positive. And then substituting like a 2 or a 3 is going to produce a positive answer. So the particle is traveling left over the time interval 0 to 1 because velocity was less than 0. All right. Now in part B, we're going to try to determine when the two particles are traveling in the same direction. So now I've already got the sign chart for P's velocity. Now I want to try to do the same thing for Q. And I'm going to try to memorize that function really quick. T squared minus 8t plus 15. T squared minus 8t plus 15. Hope I wrote that right. And the good news is this one is very much factorable. And so we're getting critical points at 5 and 3. We're going to make a really nice sign chart here for Q. We're going from 0 to 3, 3 to 5, 5 to 8. And let's plug in a 1. And I like to substitute into the factored version of that polynomial. So I could see, okay, I got a negative multiplied by a negative, which makes a positive. So we know he's traveling to the right. If I substitute a 4, I'm getting a negative and a positive. So the product is negative. And then substituting a 6 is going to give me a positive times a positive. And now we're back traveling to the right. So I'm thinking right, left, right. What I'd like to do now is kind of import that sign chart that I made for particle P earlier. From 0 to 1, we were negative. And then from 1 to 8, we were positive. So you're just kind of, and I like to stack the sign charts. And when I get these suckers stacked like this, I can, more accurately compare the signs. So what I'm thinking is right here from 1 to 3, both velocities were positive. And then here from 5 to 8, they were both positive. So that's when those particles are traveling in the same direction. We'll say from 1 to 3 and from 5 to 8, because we'll say the velocity of Q and the velocity of P have the same signs. Now, ironically, in this case, they were both positive over both intervals. There could be a situation where they're both negative over a set interval, and that would also mean they're traveling in the same direction. Jumping into part C, we want to find the acceleration of Q at t equals 2. So that acceleration is just going to be the quick derivative of velocity. So the acceleration of Q, 2t minus 8. Boy, the derivatives don't get much easier than that. You guys have done enough crazy derivatives to really appreciate that one, I bet. Substitute the 2 is 4 minus 8 makes negative 4. So we know the acceleration is negative. Now, unfortunately, that doesn't answer the question of speed in and of itself. See, the key with speed is that you want to compare the velocity sign with the acceleration sign. And when I mean sign, I'm thinking positive or negative. So what do you know about the velocity of Q at t equals 2? Well, from that sign chart we made, see how 2 sits right in here, we know that it's positive. And you could be more exact if you want to be. You could actually substitute the 2 into that function, but all we need to know is that it's positive. So now you'll notice velocity is positive at 2, acceleration is negative at 2, and I'm going to conclude that the speed of Q at t equals 2 is decreasing. In other words, the particle is slowing down, because we'll say V and A have opposite signs. Cool beans. One's positive, one's negative. Are we cruising or what, huh? All right, now D. Here is the sticky one here today. Find the position of Q the first time he changes directions. In other words, how do you know when he changes directions? That's going to be when the velocity function changes signs. And if we go back and take a look at that sign chart for Q, we would say right here at 3 is the first time we went from positive to negative. So basically, if we reword this question, we want to find the position of Q at t equals 3. Now, what you already know from the stem is that the position of Q at t equals 0 is equal to 5. And our question is, what is the position of Q at t equals 3? This one, to me, is screaming first fundamental theorem. And the first fundamental theorem says if you integrate f prime from, let's say, generically a to b, that's going to be f of b minus f of a. Now, how does that apply to this problem? Well, we're going to integrate from 0 to 3. And we're going to integrate the velocity function and of, I'll say, q. And that's going to be the position of Q at 3 minus the position of Q at 0. And basically all we want to do is try to isolate this term right here, because we already know that this bear is equal to 5. Now the real meat and potatoes of this problem is going to come when we evaluate this definite integral. So we need to integrate the velocity of Q, which is going to make 1/3 t cubed minus 2t squared. Whoops, I better check my notes. I feel like that's wrong. Yeah, that should be a 4 right there. So yeah, the original coefficient was an 8, so that needs to be a 4. And then we're going to get into a 15t. So we just integrated velocity, the velocity of Q. That's going to be the position of Q at 3 minus 5. Let's see if we can create some more room here. So I'm going to substitute the 3 first. 1/3 of 27 makes 9, minus 36, plus 45, minus substitute a bunch of zeros. Nothing better than plugging in 0. And let's see, if I clean these bears up, I think I got 18. And then I want to add the 5 over. So at the end of the day, I'm going to say the position of Q at t equals 3, which is the first time the particle changes direction, is going to be 23. In other words, the particle is 23 units to the right of the origin. So, ladies and gentlemen, hope that helps. Motion, what a popular topic. I tell you what, no matter what they throw at you, you're going to be ready.